Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on October 16, 2025, about 2 days ago. The standout claim is that it trains an image editing diffusion model with no paired examples at all, using gradient feedback from vision language models while keeping outputs realistic, and it still matches strong supervised systems and even beats reinforcement learning methods like Flow-GRPO when the same judge is used. The paper is titled, Learning an Image Editing Model Without Image Editing Pairs, and the implications from model training are quite significant. In short, this paper introduces NP-Edit, a few-step generator trained with a vision language verification loss, plus a distribution matching constraint, using millions of reference images, and it delivers competitive editing quality without curated pairs. Alright, the previous segment introduced the promise of no-pair training. Figure 1 shows the end-to-end pipeline, where a few-step generator takes an input image, plus an edit instruction, and produces an edited output. A vision language model then scores 2 questions, edit verification and identity preservation, using yes and no token probabilities, which supply a differentiable editing loss. A distribution matching DMD loss constrains realism, so outputs stay on the natural image manifold. While Figure 1 laid out the training loop, Figure 2 shows a side-by-side comparison on G-Edit bench, with the first comparison column serving as an upper bound using a many-step sampler, and our 4-step outputs in the rightmost column. The rows span diverse edits like mountains background, text replacement, dog removal, candle lighting, watercolor style, purple sheep, waving, and bamboo casing. Our results look cleaner and more identity consistent, which is most visible on the candle lighting and purple sheep rows. So, Figure 2 showed side-by-side edits. Table 2 reports quantitative customization results on Dream Booth. The table compares methods using semantic consistency and perceptual quality, and it summarizes the overall score. The 2 NP-Edit entries score about 7.1 at 4 steps and about 7.3 at 8 steps, which beats OmniControl, DSD, and SynCD trained on synthetic data. Qwen Image Edit at 8 steps reaches roughly 7.6. Overall, while its 50-step variant tops out near 8.0, so our few-step model remains competitive. So, while Table 2 covered customization, Table 1 reports local editing on G-Edit bench. The table lists model size, step count, and 3 metrics, and it shows that the 4-step NP-Edit with about 2 billion parameters reaches an overall score near 6.1 with a strong perceptual quality around 7.7. In the 4-step block, this leads the group, slightly ahead of Qwen Image Edit and Step 1 X-Edit, while Turbo Edit trails. The multi-step block remains higher overall, led by Qwen Image Edit at about 7.4. Alright, Table 1 covered local editing scores. Table 3 reports the training objective ablation. The full objective achieves about 6.1. Overall, with strong perceptual quality near 7.7, while using only distribution matching drops overall to roughly 4.9. Training with only the vision language loss collapses realism to about 3.5 perceptual quality and just 1.9 overall. Removing the identity preservation question yields around 5.8. Overall, and replacing binary with standard cross-entropy also lowers performance, so both losses and the yes or no identity check are crucial. Wrapping up, 2 takeaways stand out. NP-Edit shows that gradient feedback from a vision language model, plus distribution matching, can train a few-step editor without any paired examples, yet remain competitive. The ablations confirm both components are essential. The broader implication is scalable editing training with less curation, though identity precision and VRAM remain challenges. That is it for this episode of the AI Research Roundup. I am Alex, thanks for listening.